Okay, so I'd like to start by acknowledging the several and to many people who are working on this, starting with the scientists and engineers on our Coldtech project. This is how we got going on this building prototype hardware for Europa. But then we've expanded our group for LSIT-P for the lunar implementation. Um, this is an electromagnetic sounder. So what we do in EM sounding is to measure some combination of fields, either at or near a target object. And from that, you determine the electrical conductivity structure of the interior as a function of depth. And the main reason you want to do that is because you can get temperature and composition from those results. Now, it's not unique, so you like to combine with some other methods like seismology or heat flow, and those indeed are some of the other linchpins of a future lunar geophysical network. We're very fortunate on the CLIPS mission to be paired with the Lister instrument that Seiichi Nagahara described earlier. So the combination of heat flow and electromagnetic sounding will be very powerful on this little mission. So electromagnetic sounding of the moon was done earlier with Apollo. It was done with something called the transfer function method. And in that you use the measurement far from the moon, here from a satellite called Explorer 35, and you compare that as a reference field to the fields measured at the surface of the moon, which is the sum of the source field and the induced field. So this is all works by induction. It's not like a radar. It's more like a giant metal detector. There were several cases, depending on the lunar environment, that were looked at by different groups, and there's some discrepancy in the results. But overall, the method probed down to several hundred kilometers, maybe over 1,000 kilometers on the moon. Here is a summary of some of those results from a couple of papers by Lon Hood. He was one of the leaders of this effort. In the panel on the left, you see an envelope of electrical conductivity that by the time you look at just Lon's results or that by Chuck Sonnet or other Palmer Dials groups, you see that there's more than a factor of 10 uncertainty in the electrical conductivity from those measurements. But this slide illustrates the process of how you take that panel on the left, you take laboratory measurements of electrical conductivity as a function of temperature and composition, and you can turn that into a profile of, say, temperature gradient here on the temperature on the right, or, for example, using the heat flow, we can help bootstrap the two together for both temperature and composition. Now, the method that we're going to use is called the magnetotelluric method, and it measures the electric as well as the magnetic fields at the surface. When you do this, you don't need the distant orbiter as a reference. The measurement is complete at a single station just by measuring the orthogonal components of the electric and magnetic fields. A big advantage of this method, in addition to not needing the orbiter, is that it is very robust against plasma effects. During Apollo, it was discovered that the finite wavelengths in the plasma, which you can see modeled here on the left, these finite wavelengths basically decorrelate the distant transfer function measurement from the surface. And so it introduces errors into the sounding at higher frequencies or shorter wavelengths. So on the right are a series of panels comparing the MT method to the transfer function into a third method. This is for a uniform moon as a test. So all the results should come back looking in this light blue, and you can see that the transfer function above about 10 to the minus 2 hertz, that you start to get extreme errors. So we will be able to go robustly to higher frequencies, which translates into shallower depths and higher resolution with the MT method. The downside is it doesn't work at night in space because we rely on electric field coupling to the photoelectron sheath. This is not a problem in CLIPS because they're only daytime measurements anyway, but in an LGN implementation, we would have to do some interpolation or extrapolation over just the daytime periods to get to longer periods. What do we want to know? Well, everything about the inside of the moon. You can separate that basically the primary differentiation of the moon, which is still something that's incompletely understood. MT is not going to be so good at layering, but it will help with the temperature state and any large scale compositional gradients that may be there. I think something that we can make an immediate contribution to is the lateral differentiation of the moon. When lay people ask me about this, what's your thing going to do? I say, well, we want to figure out why there's a man in the moon. And by that, we mean, why are the Maria concentrated on the western near side? That's now known to be associated with an excess of incompatible elements, the so-called Procalarum creep terrain. And there's a couple of conflicting ideas about this, which I will simply summarize as saying a hot versus cold PKT. Is the mantle beneath this region anomalously hot, which led to the radionuclides being emplaced, or did the process that emplaced them just leave a crustal signature, and is it cold underneath? Well, in order to test that, we actually want to land outside of PKT. And so this figure on the left is from our LSAT-P proposal, and the light line is a great circle that goes from sort of the middle of PKT through Apollo 15 and Apollo 17, which had heat flow measurements.
Experience being able to see my
mute plays, which went through Apollo 15 and 17 and coincidentally passes through Mare Crisium. So the Mare Crisium idea came out of LMS originally. Most of the other payloads are agnostic about where they land, but we have teamed together with Lister, with Seiichi Nagahara, to talk about sites suitability within Mare Crisium. The heat flow wants something flat, something with thin crust, something that's easy to drill into. So Seiichi has here plotted the P-band radar, Earth-based radar for Mare Crisium, and the darker regions are presumed to be thicker regolith. So he's looking at something in those darkest regions. Mare Crisium does have two modest shaped size magnetic anomalies, which we just want to avoid for the first kind of measurement here in principle. So right now we're looking at a site sort of south of Picard crater within that 1 nanotesla contour, or sort of off on the right between the two magnetic anomalies that's still in one of those dark regions. So this is all still very TBD, but that's what we're looking at right now. So MT is a very labor-intensive acquisition on the Earth. You typically bury electrodes in the ground 100 meters apart. You use very large induction coils to measure the magnetic field. You have to dig all these holes and bury all this stuff. But our model for this, for the moon, is really the instruments that have been developed for seafloor exploration in the last 20 years, which you see on the upper right. So this is a seafloor MT unit. The electric field is measured from the voltage drop between electrodes at the end of the those big whips or booms. So a couple of several meters separation. And then the magnetic field is measured using small search coils. Those are those little black tubes sticking out. And in fact, the measurement at the surface of the moon has a lot in common with the seafloor, because we're sort of in this conductive sea or plasma and sensing what's going on in a more resistive subsurface. So this is LMS as proposed to LSAT-P. It's a very compact instrument. We use a Goddard fluxgate magnetometer that will go up on a new mast design by our colleagues at Heliospace. So this mast will go up 2.5 meters and stand off the magnetometer. The really innovative thing here, instead of using booms to extend the electrodes, we really want to maximize that footprint on the ground, that distance between the electrodes, because we'll get the very highest signal to noise by separating the electrodes even further and having them in ground contact. So the original design here shows 3 electrodes being launched ballistically. There's the little green thing is a pill. That's the voltage probe that has a wire attached to it, and it gets shot out by a spring and goes, maybe 10 or 15 meters on the moon. We measure the electric field as the voltage drop along those dotted lines in between the electrodes. Since we were selected and we saw what Stuart Bale had proposed for Lucy, which is a related measurement but not the same, we would like to go with the distributed sensors around the lander as well. And so we'd like to launch an electrode from each of 4 sides, make it look more like a traditional MT experiment, and get a very long, maybe up to 40-meter baseline for the electrodes. We've been funded under Coltech and next under IC2. So this is essentially a TRL-6 for Europa right now, which should take into account all the lunar cases. And so at the bottom there, that's the electrode launcher that's been pulled out of TVAC at Heliospace after it was tested. Same thing with the mast on the right. It was deployed horizontally for convenience. And then in the left center there, upper part, you see all the components, not in a flight configuration, but in a sort of a tableau in the thermal vacuum chamber at Southwest in San Antonio, where we did a functional test. So the LMS, to conclude, is a new kind of a planetary instrument. It's not a reflight of anything, but it has strong heritage in terrestrial geophysics for subsurface sounding, and it has strong heritage mostly in space physics for how we make that measurement. This is, I like to say, related to a space physics experiment at the surface of the moon. Our advocacy for this, namely me and Greg Delory, goes back nearly 20 years. We've been wanting to do this for Mars, but the selection of Coltech has been very helpful to get us to a TRL-6 that made it look good for LSID-P. We think that this is going to provide very compelling measurements of the interior of the moon on the second of the 2022 missions. But I'd like to still point forward to the fact that this instrument, along with a seismometer, a heat flow probe, and a retroreflector, are the core instruments for a geophysical network that we'd like to see implemented in the next decade. So thanks.
Thanks, Bob.